Okay, students, so this is video number 2 for the first lesson, which is on types of energy. I know there's a lot of time spent just talking about background information. I should go really quickly now. So back in your notes here, you're saying, how does this bomb cause matter to change? And obviously there's a whole bunch of different ways, but there's a lot of potential energy that's getting turned into kinetic energy. Bombs have a lot of stored up energy, and they release and turn into kinetic energy. We're not going to talk about what forms of energy particularly, but it's enough to know that for now. So next step. Here's a stop and jot. So in the stop and jot now, either on pencil and paper or in your guided notes, you're going to take a look at both these images here. How is the energy of a rocket before it ignites, like the picture on the left shows? How is that related to the energy it has after it ignites, meaning after it basically starts to rise up into the sky? How are they related? So sometimes we say related in terms of sometimes it's similar, or this is similar to that, or this is different than that, or this is becoming that. Go ahead and take some time to do that now. Pause your video and go on to your guided notes and begin typing inside of here. Okay, I'm going to imagine that you took the time to fill out your observations and inferences. Observations saying I see this, or I hear this, or it looks like. And then the inferences meaning, since this is what I saw, then this is what that must mean. These are things that are supposed to be supporting your explanations eventually. Okay, so if I see this and that makes me think that this is the case, then this must be why, or how it's connected. Before we go too deep into that, we still want to take some notes on what power is, just to refresh us on that as well. You might have said that the rocket is very, very powerful. And just to remind you real quick, power is the rate of work that's being done over time. So if you're using a lot of energy over a short amount of time, that means you're being very powerful. Here's the formulas that we had talked about before in case you didn't get them. And the units for power are watts. So energy is really, it's the ability to do work. If that's the case, then power is how quickly you can do the work, or basically how quickly you can make changes to matter. When you're talking about a watt, it's really just how many joules per second. It's a unit rate of joules over time. And if you remember what a joule is, it's actually, we're not going to get into that. So take a look at these light bulbs. An example of what power is and how it's connected to energy is how quickly it's using energy. You have an example on the left of a 25 watt light bulb. The W stands for watts, and a watt is a joule per second. So it's 25 joules of energy being used every single second by this light bulb. And on the right, you have a 60 watt light bulb, which means it's using over 2 times as much energy per second. Now, some of the energy is getting turned into light here. Some of it's getting turned into heat, or into thermal energy, I should say. You may have seen a watt-hour meter like this. This is basically just something that measures the amount of energy that's being used per second. So they can, just energy that's being used altogether, I guess, so that they can charge you money for that. But just a couple interesting things about this. You'd say the energy that's being produced from this isn't actually being produced from this. It's coming from somewhere else. It's an interesting concept for later as well. That energy can't just be made out of nothing. It's not like this light bulb is just more energetic. It's getting that power from somewhere. And electric companies will charge you for every little watt and joule per second you use. And I think one of the reasons why you'd have to think about that in that way is if electric companies charged you just for how much power you're using, say you have a really powerful blender, right? You might be using very many joules to power that blender, to move a lot of matter inside of it with a lot of force. But you don't use blenders all the time, right? It might be a 3,000 watt blender, or probably 1,000 watt blender. You don't use it that often. So if you're using 1,000 joules for just a couple seconds, you shouldn't be charged for 1,000 joules as your maximum capacity. You just get charged per second for how much you're using. So it is kind of fair, but that's why you shouldn't run a toaster to heat up your house. It's not very good at doing that. The formula for power is work basically divided by time. And in our case, we can think about it in terms of energy. So anytime we know how much energy is happening, if we can divide that by time, you have power. So an example over here that we went through in class before we left, you had work being done to this box. It's a box that requires 12 newtons to push over 5 meters, which means you've used 60 joules of energy. Now, if you're timing how long it takes, that can tell you how many watts you've used, basically how many joules per second. Just all that to say, we're not going to talk about power very much from here on out, but to refresh us, it's been a long time. So once again, work is how much energy is being used to do something. Power is how quickly that's being used. Now back to energy, types of energy. Finally, we're getting to this. Lots of review. There are two types of energy. You could say types, you could say forms, but for our sake, we're going to say types. These two overarching things, kinetic and potential. Kinetic is the energy that is in motion. I call it the energy of motion. It's really a measurement of the average motion inside of even the molecules, but on the large scale, you use many different ways to calculate it. And then you have potential energy. These are the energy forms that aren't actually moving currently, as far as you can see, but it has the potential to cause a lot of motion. Okay. So some of the actual forms of energy that you might be thinking of when you heard about energy earlier: chemical energy, motion energy, sound, heat, light, electrical, nuclear, gravitational, elastic, probably some other things like renewable energy, which isn't a form of energy, but it's just a description of different forms of energy that we can get more of in our lifetime, compared to, say, like fossil fuels, which burn up and then we can't get more of them. So we're going to go through these in depth. Make sure you pause and go back if you need to check your work, and make sure that you're taking your guided notes. If you are keeping guided notes like we are, we should be done with the notes on power and starting on potential energy notes right now. Okay. So potential energy. It is the stored energy. It's the energy of position and condition. So we say you can have stored up energy sometimes on Earth, because if you go up, like my pencil's up in the air right now, the higher up it goes, the more energy it has when I release it. Not exactly when I release it, by the time it gets down. It actually has the same amount of energy always, but the idea is I'm storing up the energy, and the energy is getting turned into motion. So because it has the potential for being in motion, we call it potential energy. Just the same as, say, a rubber band. The rubber band, you don't have to take it up here to give it energy. If you stretch it back, right, it has energy now. It's a it's a conditional potential energy. So it's not about where it's placed, its position. It's actually about the actual molecules themselves being stretched out. Springs, sometimes even, say, like a gasoline can that has gasoline in it. It's the condition of those molecules and their ability to blow up that gives them a conditional potential energy. So all that to say, potential energy is stuff that's stored. If it has the potential to make matter change in some way, it's a potential energy. So think about a spring. If you have a spring that's not relaxed, it's not compressed, or it's not stretched out, it's just staying there, it doesn't have any energy. Not positional. Unless you lifted it up in the air and gave it gravitational potential energy, no potential energy. However, if you compress that thing, or if you stretch it out, it has potential to move back again, to change the matter of itself. So it's potential energy. If you stretch it more potential energy. Compress it more potential energy. It's the same idea as if I have a pencil, the further up I go, the more potential energy I'm giving it. Examples of this might be, like we said, the rubber band. If you're stretching it more and more, it gets more energy that allow you to shoot somebody faster with it. Or a roller coaster. Roller coasters get a tremendous amount of potential energy by pulling a huge cart up a big hill. The further up they go, the more you can move. And the only way you can move is to have the energy in the first place. So the energy gets stored up as potential energy until it reaches the top, and then it gets turned into kinetic energy. Kinetic energy is the energy of motion of waves, electrons, atoms, molecules. Basically, you don't see that stuff though, so it's the energy of objects. It depends on the mass and speed of an object though. So the more mass it has or the more speed it has, it's going to have more kinetic energy, more of an ability to change whatever it ends up hitting. If you think back to the law of conservation of momentum or Newton's second law of motion, force equals mass times acceleration, they're all related. If this person's moving faster, right, he's just got more energy, period. It's more mass. If he was a 6'9" linebacker, linebacker would be nice, offensive lineman on the Eagles, doing that as fast as he is, you'd have to have more energy. Or if you're trying to create a huge explosion like this, lots and lots of energy. And if it's actively moving, once again, it's kinetic energy. And you have to say, well, where is he getting that energy from? He's getting that from stored up potential energy, probably from the food he ate earlier that day. Okay, number 3 does not fit into our scheme. We said kinetic energy and potential energy. All the forms of energy that we know about fit into those 2 categories of either being stored or currently moving. But dark energy does not. Dark energy we just have no clue about. So it's obviously moving stuff out there. That's basically all we know. So if you remember back to your galaxy reading from the eScience, the last one I think we did, the expansion of the universe, there is something that is causing the universe to expand. We have no idea what it is, so we're just calling it dark energy. Maybe you'll find out in a couple hundred years, or in your lifetime, hopefully. Okay, so just a quick check here for the rest of this. You got to tell me, take a pause and think about it for each of these. Potential or kinetic? Take your pause. Okay, it's potential. It's a conditional potential energy. The bow is storing up energy in the actual wood fibers, and when he lets go, it's going to turn the arrow into lots of kinetic energy. Okay, potential or kinetic energy? Pause. And we're back. This would be considered kinetic energy. Maybe she's hopping up in the air, so she has some potential to come back down again, or she's going downhill maybe, but mostly we're going to say this is an example of somebody in motion. Her muscles are creating kinetic energy to move her body. Potential or kinetic? Pause. And we're back. This would be a consideration of it's not moving. It's not about to fall anywhere. It's actually the opposite. It's going to go up because it has a tremendous amount of potential energy stored up in the fuel inside the rocket. And this would be a picture of that energy being released. But it's not just kinetic energy. In this case, you think about this. On the ground, there's only a tiny little bit of fuel that's actually been used so far. So most of the energy in this rocket is still potential. And it's going to be potential until it gets close to, outer atmosphere. At that point, all of its energy that was potential energy in the fuel will be turned into kinetic energy. So it can be turned from one thing into the other. The skateboarder, potential energy, right? He's not currently moving, he's at the top of the arc, and as soon as he lets go, it will be turned back into moving energy. And take your guess on this one. Probably you can observe she's moving downhill, so she's probably got some potential energy, but mostly kinetic energy. And pitchers. Pitchers generate a tremendous amount of kinetic energy using their muscles. They really get the ball to move fast. That's what the idea is behind changing the objects. All right, one last little thought here. If you've ever seen a roller coaster before, if you know how this works, the total energy in a system doesn't really change. If the car has this much energy up here to begin with, 100 we'll say, right? And it's kinetic at first. Then as it goes up, it gets stored up. It's not like it just disappears. The further up you go, it gets stored up as potential energy. Because if you were to turn right back around, you'd be able to fall back down that hill. So if you notice, at all times, these two, the potential energy plus the kinetic energy is equal to the total energy. And a lot of times they call that the mechanical energy of the system. We're going to talk about that more when we talk about it in our third lesson called conservation of energy. But for now, go ahead and take care of making sure all your guided notes have been taken and click on the Google form to submit it for your grade for this lesson. Take care.